Welcome back, friends and neighbors. It's now time for another networking video from the RIT Networking Labs. I'm your host, Bruce Hartpence, and so without further ado, here we go. You know, sometimes in networking, weird stuff just happens, and that's one of the things that makes networking so fun. And so today we're going to investigate one of those weird things, or maybe what I like to call, what the heck is happening? Or maybe even adventures in networking. But before we do, maybe a little reminder about some of our networking history or our networking protocols. We've talked about Ethernet before. I wrote about it in Chapter 2 of the Packet Guide to Core Network Protocols and, of course, in the videos that I've done on this channel. And from that information, we know that Ethernet frames have a certain structure. They're built in a certain way. And one of the rules that we have is that Ethernet frames can carry a maximum of a 1500 byte payload. Now that assumes you're not doing jumbo frames, and that's still not as common as the 1500 byte frame limit of your standard Ethernet networking interface card or networking switches and routers and things like that. Now, what does that mean? When we say the payload is 1500 bytes, we're not taking into account the rest of the frame. Now, depending on what you're looking at or what fields you're taking into account, you might have actually different sizes for the frame. So let's talk about that for a sec. The payload is 1500 bytes, but if we add the source and destination MAC address, 6 bytes each, and if we add the control field, that's another 2 bytes, we get 1514 bytes. And that's a very common size that we see in frame captures like Wireshark. If we add the preamble and the CRC, which can't be read by a lot of packet capture software, then we get to 1526 bytes. And so that's why a lot of times when you're reading documentation, it'll say that an Ethernet frame has a 1526 byte size. In between one frame and another, there's this thing called the interframe gap. You can't just tail end one Ethernet frame to another. You have to wait an interframe gap that's about 12 bytes in length. So that gets us out to 1538. Now the interframe gap is not actually considered part of the frame, but there we have it. So from Chapter 2 in the Packet Guide to Core Network Protocols, here's figure 2.4 or 2-4, and this just shows you the fields that we have in Ethernet. And so we've got our 8-byte preamble, the 2 MAC addresses, the control field, our data field. Now remember, that's variable size. It can be much smaller than 1500 bytes, but 1500 bytes is the top end. And then we have our 4-byte frame check sequence, or CRC. And for right now, we'll forget about 802.3 versus Ethernet Type 2. They're the same size, but they use their fields in a slightly different way, and they have slightly different uses. So let's get a little bit of proof via packet capture. What I've got for you here is a collection of frames. I just did a normal capture on a set of devices. And what we're looking at here is some TCP, some DNS traffic. That's UDP. We've got some HTTP, also happens to be TCP. There's even an IP version 6 frame in here. Now, the important thing that I wanted you to get out of this is that the length of all of these is 1500 bytes or less. And it doesn't matter whether you're doing IP version 6 or IP version 4 because they both fit inside an Ethernet frame. And Ethernet frames have a top end of 1500 byte payload. Okay, so what I did next was start up a file transfer to move some big data around. So in moving my chunks of data around, we can see that in this case, the source was 10.160.100.56. So this data is moving from this particular machine. And because it's transferring a large amount of data, it's filling up those Ethernet frames. So the payload is topped out at 1500 bytes. So that's why we see a length of 1514 here. Now that's important to us because that sort of verifies the information that we already knew. We have 2 MAC addresses, the control field, and then our 1500 byte payload. And so that's what's happening here. And that's what you normally would expect to see in a large data transfer. And here's where we come to the point of this video. What the heck is happening here? There's 3 pieces of information that I want you to look at. First of all is that top line where it says that the length of this particular datagram is 10,054 bytes. That's crazy. And then if we look at the total length indicated in the IP header, we can see that it says that it's 10,040, of course excluding the Ethernet fields outside of the data. And then down there below, we can see that there's a data inside this TCP of 10,000. So it's not 1040 or 10,040 because both the IP header and the TCP header are both 20 bytes. So we have 10,000 bytes carried in this IP packet that's inside an Ethernet frame, and we know that just can't happen. What is going on here? Well, to understand this, we have to remember a couple of things. One is that packet capture software often gets to the data or the data that was moving across the network after the NIC is done with it. That is the network interface card. Wireshark is no exception to this. The other thing we have to remember is that many network interface cards improve performance by handling several tasks. Remember that there was a time when a network interface card was just this interface that gave you the mechanical and electrical specifications for connecting to the network. It did no processing. The same is true of video cards. The more fancy your video card is, the more processing it does, instead of having to hand all that stuff to the main or central processing unit in your machine. What we're seeing here is the impact of the NIC doing work for the system that's connected to the network here. In this case, we're talking about large send offloads. It means that the NIC is trying to do the segmentation and reassembly for you. That you take a large packet and instead of having the very traditional operating system parse it, the driver, this monolithic driver, we're handling a lot of this stuff on the NIC. And so we can get to this stuff on the Advanced tab after you go to the Configuration button on your network interface card. And so here I've just circled the 2 things that are the offloads that we're talking about. Now if I disable both of these, then Wireshark behaves in exactly the way that we would expect. No frames get to Wireshark that are larger than 1514, and everything is back to normal. Well, there you have it. That's the mystery solved of the gigantic frames. Now remember that this is not an example of jumbo frames. And even if it was, the jumbo frame is 900 or 9,000 bytes, so it doesn't even match up. What we're looking at here is NIC improvements. Well, thanks very much for listening. Thanks for watching. Hey, if you like this video, if I helped out, go ahead and like the video yourself or subscribe to the channel. Thanks again, and may your packets always reach their destinations.